Okay. Hello. Good morning. I will just explain today in the start about this content what I will be covering. So first of all, myself, Dr. Javed, and I will be looking after some of the content for this topic, material characterization. So as you have already some lectures, for this content with Dr. Swift and Dr. Karthik Ugyani. So I will just explain you what I will be doing and how you will be accessing the information. So this is the material characterization main page. So if everyone can see, yeah. Okay, so here at the bottom, so it's this content with my name, and here I will be adding all the content for this semester and what I will be teaching. So here in this, you will be getting PowerPoint slides in advance, and that file will contain all the content for the lecture which you will be covering in our synchronous sessions. And there will be one audio file that will be related and that will be discussing all the slides what you have in your lectures. So what you have to do, so that you open in this PowerPoint file, and then you just run this commentary, that audio recording. So I have done this all the audio recording for this lecture. For instance, so this lecture has two parts, X-ray scattering and light scattering. So I have done first part. So I don't want like I give like 2 hours videos here to bore you so much. So I just want to give like at least that content that you can basically understand easily. And then the topics which are more complicated or complex, I will explain and go through in these lectures, because these topics they are in quite detail, so you need more focus and more work while we are doing the synchronous session. Okay, so always you will be getting this PowerPoint file. So you have to open the PowerPoint file, and then you play this audio recording, and then you can easily see. And this you can open even in mobile. So it will not give you like so much problems with data and everything. So it's just MP3 audio file. So this you can access easily from your mobile data or iPad data or whatever you have access either from the computer. And then there always we will some files related to the topic. For instance, this lecture has this one article which is small angle electric scattering, and how we can calculate the interaction energies between different bio macromolecules. So I am expecting from you, so before lecture, so you must go through the slides along with this audio file, and also go through this article what I submit, because these sessions are free based lectures, and in this these are mainly called student led sessions. So if you go through the slides, and if you have any questions, so you can email me in advance, and then I can address those questions in these sessions. In addition to that, I will be discussing in these lectures some of the topics which are more complex and which need more attention from you. So I will just explain those topics to you, and some additional topics which I will not be uploading the videos. So that we will be covering in this session. So these sessions will be very important for all of you to join. So because we will be doing some important topics which we are not covering in the audio recordings, and also some problem solving sessions. So for instance, I will be adding some of the questions related to the today's topic, uh, and that you can also see in this part, that question what you will be having the and that you need to solve after this lecture, because I have to go to the lecture, and then you can go and try to solve those problems. And then in the next session, just before I start the next session, I will be just giving you quick feedback for the previous session. So for instance, whatever question you will be doing today, you have to do those complete those questions and just email me. Yeah, then I can give you quick feedback by email, or our in our synchronous sessions. So that's how I will be just running this session. I think we have like 6 sessions in total that we will be doing together. So any questions so regarding to access the information, and uh, how we will proceed with this teaching. So any question or anything which you are not sure, please let me know now, and then we can, otherwise we will start this our session today. And this information, by the way, can also be accessed. Just try to get this information from home section, and also more detail. I think it will be good if you go to modules, and if we in the go in modules towards the very end here, you will see that this session contains all the information. The more detailed information will be in this section, yeah, where you will see all the papers and articles for the future, yeah. So try to focus on modules in this semester, in the module section on your Canvas page. Okay, any question, anyone? So,
No, sir. Thank you.
okay, that's good. So now I will just to quickly want to check with you, how many of you or everyone can just say yes or no that if you have already seen the slides and listen the audio for those files. Can you everyone please confirm now that if you have, or yes or no, you can just answer me so that I know that what is the statistics and how I should proceed with the lecture. So Aman,
No.
Moin, Moin.
Hello?
Moin, did you see the slides or audios?
No.
Najima, if I'm pronouncing your name correctly, Nagima.
I've looked at the slides only.
Ahmad.
Just
I
the
just have a
slides.
quick look at the
Okay, thank you.
video, but not in details.
Yeah, no worries. Bronte.
Yeah, I went through the slides and the audio.
Okay. Okay. Yep. Yeah. Please. If I'm pronouncing your name, you don't feel shy. Please correct me. Yeah. I just want to be. Yeah. To pronounce your name correctly. Yeah. It can be. I'm not pronouncing right. So please correct me. Yeah. Don't feel shy. Alles vegan. Or all vegan.
I think we're trying to call me. It's Oluwasegun, but you can just call me Daniel.
Daniel. Okay, Daniel. That's sorry about that. Okay, so did you have a chance to look at the slides?
No, not yet.
Afia?
Oh, no, sir.
Okay, so it's okay. It's our first round, so first session. So it's fine for me for this one. But for the next sessions, please do see all the lecture slides and the audio recording. And if you play the audio recording, that you will see that it goes along the slides. It goes discusses all the slides one by one. That's how you will be just focusing on your lectures. So anyway, for today's session, so I will just I have only done the there are two parts for this lecture, yeah. So that is light scattering and X-ray scattering. So I have explained in quite detail about the light scattering, yeah. So intentionally I didn't do the X-ray scattering video because I knew that most of the students they don't get a chance to look at the slides. But these topics are very very important, so I wanted to just go through with you in this session, yeah. Okay, so what we are doing in this session, so we are discussing about the small angle X-ray scattering. So scattering, you must have read or known about this fact that scattering is just that when you have a light and it hits any object and it then travels to all directions, it diverges to all angles, and that process is called the scattering. So, and we know light has energy and it can move in the waves, in the form of waves, and also it can act as a particles as well. So when it hits any object, so when it scatters, so this scattering has quite huge information. If there is some way that if we can detect that scattering and we can get that scattering pattern, that gives us the information about the molecular structure of the system what you are studying. And also under certain conditions, if you have a lot of particles in your system which you are studying, how those molecules they interact with each other, that information is also hidden in that scattering pattern. So what we are focusing in this part in small angle X-ray scattering, that instead of using light to hit an object, yeah, we use X-rays as a light source. Yeah, X-ray is also part of light. So we use X-rays to shine on the particles, and when a particle is interacting with the X-rays, what it happens, it scatters light. And in case of inelastic scattering, which is also called Rayleigh scattering, in case of light scattering, so the scattered light has the similar energy as the incident light. So it means the X-rays what you are shining on your object and the scattered light which is you achieve as a scattering pattern, they both have the same energy. So this is called the inelastic scattering. So in this case, the energy of incident beam and the energy of the scattered beam, they are equal. So in small angle X-ray scattering, what we measure those scattering patterns, that what light is scattered. Yeah, we measure the intensity of that light X-ray radiation, which depends upon angle, scattering angle. So if you have a light, we will explore in the next slide. So it goes in a straight line and then it hits object and then it scatters to all different angles. But when it scatters, the scattering pattern at very low angles, it contains the information for the structure of material. And we can get a lot of information to study the macromolecules. For instance, it can give us structural information about particles, which means it can give us information about radius of particle. Yeah, what is the size of particle, and that comes from the form factor of the system. So form factor is usually the scattering pattern from a single molecule. And from that, we can calculate the radius of gyration in solvated conditions. For example, if you have a protein in your body, so it will be always solvated in water. So in that case, we can calculate the radius of gyration. So from that, we can calculate the radius of molecule, protein molecule. We can calculate the radius of polymer molecule. We can calculate the radius of any spherical emulsion or spherulites using this technique. So we use usually radius of gyration in very ideally dilute solutions, so where molecules are not interacting with each other. And also we can calculate the shape of the particles, which are in range of 1 nanometer to 100 nanometer scale. So this is very useful technique in contrast to light scattering, so that we can calculate the shape of the particles as well. And also we can calculate the intermolecular interactions between different particles. For example, if you are two polymers, how they interact with each other, what is their interaction energy between them. If two proteins molecules are there, what kind of interaction energies between them are there. And those interaction energies are quite important to formulate different materials and to study different properties of the materials. And also it can go get some information about some clusters in medium to high concentration. So this is a plus point as compared to the light scattering which you have studied. So what we do here, so that is actually totally explained in more detail here in this slide, that what small angle X-ray scattering does. So what we do, for instance, we have a system in which we have dissolved different polymer molecules or some emulsion molecules or some drug molecules or some protein molecules. So this is your solution. And like UV visible spectrophotometer, so when you do two kind of experiments, in one experiment you do just the solvent, and another experiment you do solvent plus your molecules. So in this case, what you do, you shine a light, and in this case the light is X-ray, and that X-ray has certain energy. Yeah, that is called the primary beam or incidence beam. And that energy, you always know, that is inversely proportional to the wavelength, and that is the incident beam, and that is expressed here K0, that is the primary beam, is equal to 2 pi over lambda. So that is the energy of the primary beam. When it hits the protein molecules, polymer molecules or other molecules, what it will happen, it will scatter the light in all the directions. Yeah, and that light will give you a scattering pattern. So this, you can see this circle, so that all different dots here, they are different scattering processes happen. Yeah, so it's scattered, and all these circles, what is shown, for example, here. So these are all the dots, what it scattered the light X-ray, and you got this scattering in this one. So this is the primary beam, incident beam, and this is the same incident beam that will also hit this detector, for example, where it will just form a spot here. And then you will see all around it, you will see scattering at various angles. So various angles, you will see scattering. And in this case, you will have another vector, another beam, you can say that scattered beam that has called K1. So this is the scattered beam. So you have primary incident beam that is K0, and this you have a scattered beam. So this K1 is also the same energy as you have the K0. So that is also expressed as 2 pi over lambda, that is in this case K1. So in this case, we provide X-rays, yeah, and we get the scattering pattern that is shown here. And then the scattering vector from both these waves will be equal to subtraction of scattered wave minus incident beam. That will be the scattering vector what you achieve from this. And that can also be expressed in terms of Q, yeah, that is 2 pi into S, and that can be explained also in terms of Q. So Q will always be equal to K1 minus K0. And that in this case will be is equal to 4 pi over lambda, because 1 is 2 pi multiplied by 2 pi, that is 4 pi over lambda sine theta. So that depends upon the angle. So the scattering vector actually gives us the information that at different angles you got the scattering processes. And in case of small angle X-ray scattering, our main focus is to focus on very, very small angle range from 0.1 to 10 degree maximum. So even 10 degree, we don't go that in normal instruments, we just go from 0.1 to 5 degree angle. So this is what we do. We get scattering at different angles. As you can imagine, so this primary beam which goes, and if it hits this part, intensity that counts of these X-rays what are hitting straight away, this will be very, very high. And the scattered beam, the number of counts, how many photons have hit the detector, that depends upon the angle. At various angles, there will be different kind of number of photons hitting the detector, and that depends upon your molecular structure. So if your X-ray beam is hitting very dense particle, dense atom, for example, iron in the molecule, it will scatter more. If it is hitting hydrogen, it will scatter less. Yeah. So this means all this information, what you will get, that you will be depending upon the scattered photons, and that information is quite important. And this is in contrast to the light scattering, where you just go from 10 degree to 180 degree. So in light small angle or small static light scattering, you just go very, very high angle, and that gives different kind of information in contrast to small angle scattering. So what we do here, we shine the light, X-rays, it scatters, and then we get scattered light at various angles, and we get intensity of scattered light with as a function of angle. And in that case, our function of angle is hidden in this vector, which is called the scattered vector, that is called Q. And Q has the information about angle that you can see this 4 pi over lambda sine theta. So this is our information. So now we have scattering vector Q, which in simple terms you can say it's angle, and you have intensity as a function of angle or as a function of scattering vector Q. So these are the two factors which contains the information about the structure of your molecule. Yeah. So, and now we need to understand the theory of scattering, that how this intensity has the information about the structure of the molecule. So from theory of scattering, from the physics behind the scattering, we know when any wave is achieved by the scattering process, so we get the amplitude of that scattered wave, yeah, and that amplitude of scattered wave can be small or high depending upon the source from where it's scattered, yeah, and that amplitude depends upon the scattering length density. So that depend upon this factor delta rho, and that is called the scattering length density. So here you see this complicated equation. You don't need to remember this equation, but need to understand what we are achieving from this. So the amplitude of any scattered wave depend upon the scattered length density that is shown here. Yeah, delta rho. So what is the delta rho? So this is the excess scattering length density. So if you go back, so here you see, here you have protein molecule, for instance, and here you have water molecules. In protein molecules, you can calculate the scattering length, and water molecule, for instance, you can calculate the scattering length, and you subtract both. This is called the excess scattered length density. So, but what is scattered length density? So that is the number of electrons multiplied by their charge. So that will be the scattering length density. So it means the scattering that depends upon excess scattering length density depends upon the number of electrons in the system. How many electrons will be in the system, that much will be the scattering length density. That will be the, because X-rays scatter from the electrons. So if there are more electrons, the scattering process will be more. And the difference between scattering length densities of your macromolecule minus your solvent, that is called the excess scattering length density. So more the scattering length density, more will be the amplitude of the system. Yeah. So this is one factor where it depends, scattering length density as a function of their R. So add function of distance. At all the distances, whatever is the scattering length density, that is the one factor which will tell you how much quickly you will, how much high you will get the amplitude of the factor. Yeah. And also it depends upon if you have small molecule or large molecule, that will also give you the different amplitude values. For example, if you have large molecule, R will be high. Yeah. And if R is high, the amplitude will be higher as well. So this is, and this is all the scattering length density in your molecule and all the distances in your molecule. If you sum up to the total volume of your molecule, for example, total volume of protein, total volume of molecule, if you integrate all the scattering length densities and all the distances as a function of your scattering vector Q, what you will achieve, that you will achieve the amplitude of the scattered wave. So this is the physics of scattered wave explained to you. And in this case, your delta rho, it is the excess scattering length density that we have discussed. That is the scattering length density of your molecule. It can be protein, it can be polymer, it can be some spherulite, or it can be any particle what you are studying in solution, minus scattering length density of your solvent. For example, if your protein is in water, water will be your solvent. So the scattering length density of water will be subtracted from this, that is excess scattering length density. This is the physics behind of scattering process, that what is the amplitude of any vector of any wave, which depends upon their Q value, you can calculate from this equation. But what we measure here in the previous slide, that we see here, that is we get the scattered intensities at different points. This is not the amplitude. The small angle excess scattering measures not amplitude, but it measures, the detector has not the ability to measure the amplitude, that how high or low is the amplitude. It can measure only how intense is that spot. Yeah. How many photons have hit that. And that information is calculated by small angle X-ray scattering experiments by the detector. So detector measures only the scattered intensity. And also we know from the physics of waves that scattering intensity is actually function of amplitude as a function of angle multiplied by complex function of amplitude as a function of Q. So it means scattered intensity is actually the proportional to the amplitude square, in rough terms you can say. And it depends upon the total number of photons which scattered in different directions. In different direction mean at different Q values. And this is isotropic function. So this function is same, that in every direction it will be a product of AQ multiplied by AQ. It's, you can say it's amplitude square. And then if you have molecule which has lot of atoms and lot of electrons, and sum of all the electrons, yeah, if you average over all the molecules and the scattering in all the direction, if you average over all the directions, that will be included information in this intensity of Q. This is how you correlate the structural information with the scattering process, with the number of photons and with the amplitude. So it means your IFQ has the information about the structure because it is happening due to the number of electrons and how those number of electrons are distributed in space at different distances. And that's why we just sum up over total volume of the system, and that's how you calculate the intensity as a function of Q. So in this case, I will just go now. So this is the process what we do. So in this case, we use X-rays, and X-ray is our source of light. In our lab setups, we use different kind of instruments, and those are called point collimation instruments. What we do here is the source of light, how X-ray is actually bombarded to the particles. In this case of point collimation, so these instruments have a X-ray source, X-ray generator that generates X-rays from the X-ray tube, and that X-rays then pass through a pinhole, and that shape of the pinhole actually decides the shape of your X-ray beam. So usually we have these pinhole that are very, very small circular holes. So that's why when X-rays pass through these, you will get a small beam, small circular beam, or kindly slightly elliptical spot that you will achieve from this pinhole collimation instrument, and that will go and illuminate your sample. And usually this area is very, very small, so these beams are not very powerful. So these beams, X-ray beams, primary beam intensity is very, very low. So this is not very intense or powerful beam which has less energy. So it means if it has less energy, so when it will hit any molecule, protein molecule or your polymer molecule, it will scatter light, and that intensity of scattered light also will be small because your primary beam intensity is small. So it means in this case, your scattering pattern will not be that good. So you will get very, very light spots and by the detector, and that your data quality will not be very good. So in this case, what you do, so because in this case you measure intensity as a function of Q. At different angles you measure intensity. So what you do, you start your experiment, for example, from angle 0.1 degree, and then you give this, set the time that it should hit the particle at 0 degree angle for 1 hour. And then after 1 hour, it will keep on attacking this particle, and at 0 degree, you will get the scattering pattern. And then you just move that it goes to 1 degree. Then again, it measures for 1 hour, then 2 degree, 3 degree, 4 degree, 5 degree in small steps. You give a lot of time because your intensity is very, very weak of the incident beam. So you give more time that it can scatter more and more. And then you get a visible spot, which is like detected by the detector, and you get good counts as a signal. So this can take weeks or days to measure an experiment. For instance, during my PhD time, I was measuring some proteins, and one sample I was doing, it was taking more than 24 hours to complete one sample. And imagine if you're doing water, that will be taking 24 hours to measure, and take some protein, one concentration. Yeah. So if you're measuring like multiple concentration, so weeks and weeks will go, and you will be just doing one set of experiments in maybe 1 month. So this is not a good setup for small angle X-ray scattering. So then scientists have, because in this case, you have cutting the beam actually in both directions. Yeah. So you are getting one narrow spot only. But instead of using this point collimation, scientists have developed one setup system called the line collimation. So in this case, you restrict the beam only in one direction, not in both directions. So it means it will not be only circle, but it will be act as a line. So it won't be a point anymore, it will be a line. So it means you will have more cross section. Yeah, and that is long, but it will be narrow line. And it means it will have intense light source as compared to just one spot. And in this case, when you have this line collimation instrument, and that will have very intense energy, and that when it will hit the particle, this will give you scattering intensity very, very good as compared to the point collimation. So in this case, you don't need to wait for every angle for hours. In this case, you can go to complete the whole experiment in minutes, for example, 20 minutes or 30 minutes. And that's how you can use small angle X-ray scattering to measure your polymers or proteins or other solutions. And these are the two systems which are shown here. For example, this has Biozux 100. This is one company which is, I think, from Austria, and they make from this point collimation. And another company is from France, so they have made this research instrument. This is line collimation. This is very intense powered instrument, and this can measure the sample in minutes, like 10 to 15 minutes. But also there are some centrally located facilities which are called the synchrotron sources. For example, that is one we have in Oxford, near Didcot. That the synchrotron facility is called Diamond Synchrotron Source. So this has a big ring, and that can generate very, very high power X-rays, and those X-rays actually can pass through different slits and setups, and that can come to your beamline setup, where you can have your sample solution and your solvent solution, and then you get your scattering pattern. This is on the detector. They have different kind of detector. Yeah. So this is one of the beamline, I22 beamline in Diamond Synchrotron Source, where you can do all these experiments in 1 to 10 seconds. So you see, you can measure some sample in weeks times, and if you have high energy beam, you can measure same sample in seconds time. So there are different setups available for doing the X-ray scattering. So what information what we get from this small angle X-ray scattering, and that's the first most important thing, is size and shape parameter evaluation, what we can achieve from this molecule. And how we link the intensity to the structure of molecules, we have partly done it, and we will just go a little bit in more detail that what we get from this, and how we can correlate that information from the scattering to the radius of the molecule, or the size of the molecule, or the shape of a molecule. So we have seen that intensity is a function of amplitude multiplied by amplitude, and that is the sum of overall volume, like the overall area, that is the intensity of the function, overall volume of the particle. So that is your intensity, what you achieve. And we know that is related to the excess scattering length density. Yeah. So this is excess scattering length density of A multiplied by excess scattering length density of A star. Yeah. So this is the two functions what we have, giving more inputs in this one. And then it depends upon I of Q, that's function of angle, and R minus R prime. Yeah. So these are the distances that from center of the molecule to the end of the molecule. That will be the total distance any molecule will have. That will be your, you can say, radius of the molecule. Yeah. From center to the end. And that goes in small step, D of R into D of R prime. Yeah. So in small step, if you sum all of these, so that will be your total function that will decide how much you will be scattering intensity. So this equation looks quite complicated, because we cannot straight away measure from this the radius of the particle. What we have to do, so when we have any particle which have lot of electrons at different distances, so what we do, so if we know the information about their scattering length densities at the different distances, we can integrate the whole function from distances 0 to the total distance of the diameter of the particle, that we can integrate this one from 0 distance to d max, that is the total distance of your particle. And that is related to their function r square, that is the radius of the particle, and that depends upon sine q of r, that is the angle, over q of r, and d of r, that is the, in the small steps it can go. So this is the total function, you will get the scattered intensity. Here this gamma of r, you can see it gives us you the relationship between different scattered photons from different electrons, how you can correlate with each other. That is called the autocorrelation function of your excess electron density, that is shown here, delta p of r, delta p of r, and that is now hidden in this autocorrelation function of your system. So this means from intensity you can calculate the size of the particle, that is the radius of the particle, and that we use usually one simplification of this equation, and that is called the Grignard's approximation, how we can find it out. Because this information, you can see that it's having this term that we get the intensity from 0 to d max. D max, we can know what will be the d max possibly, but can we have this angle 0? In reality, we cannot have angle 0. Yeah, so we will have 0.01 or 0.02, that will be the minimum angle. Yeah, 0 angle we cannot measure, because 0 angle in this case is the angle where incident beam hits the detector, and that is the primary beam. That doesn't have information about the scattering. So in this case, what we do here, our experiment, what we do, we take, for example, our solvent, for example, water, and then we measure, put it in the small angle X-ray scattering setup, and then shine X-rays, and then we get scattered intensity at different angles as a function of Q. So at different angles, that is represented by Q here, and you will get different intensities. And that is one of the sample which I was doing in my PhD time. So that I got like different scattered intensity from, in this case, it was buffer in the water. Yeah. So this is the scattering intensity pattern. So you can see at small angles, you see very, very high intensity. Yeah. And at very large angle, yeah, you see very, very small intensity. Yeah. So that is the first thing what we get. And then what we get, then we measure add your protein in your buffer, and then you measure the scattering pattern from the solution. And that you can see looks quite different as compared to the solvent. And this will be your scattering pattern from your buffer. This will be scattering pattern from your protein plus buffer. And as we have done, so the difference between them, that will be your sample scattering. So this minus this, that's the curve what you will get. This is called the background scattered intensity from your system. And this is how you get a scattering pattern from this. And this pattern actually contains the information about the structure and the shape of the molecule, and that we will see how we do it. But before I go to that, I just want to tell you one very important point here. So in this case, that you can see that Q, what we are getting, yeah, that is 4 pi over lambda. So lambda is wavelength. Wavelength means it's a distance here. So this is scattering vector what you are getting. It's inverse of distance. Is it right? Yeah. So lambda always wavelength is in nanometers. What we use, for example, light, it has 400 to 800 nanometers in case of visible light. And in case of X-ray, it's 0.1 to 0.2 nanometer. So these are nanometers region here, wavelengths. So it means this Q vector, scattered vector, it's actually in inverse space of distance. So it is opposite to the distance. For example, if in this case, large distance will be small Q value and small distance will be large Q value. So, and now if I come to this part, here you can see here the small Q value. So this means it is the large distance value. Information in this part will be about the large distance in the molecule, and that in one way you can say the maximum distance Dmax in your molecule. The Dmax information will be hidden in this part. It's a small Q value because it's a inverse space. It is 4 pi over lambda. And information at high Q, it will be for smallest distance. So it means that will be inside your molecule. Like for example, if 2 electrons of 2 atoms, they are scattering intensity, or very, very hydrogen atom, carbon atom, what is inside the molecule scattering intensity, that information will be hidden here. So for you, most important part to calculate the size is this part where you have small Q value, because that will give you information about the Dmax of the system, maximum distance in the particle which it can be. Okay, so is it clear? Any question until now? Okay, so now we will see that now we have this background subtracted intensity. Now how we can calculate the size of the particle. So we can, this equation we can simplify. Yeah, we don't need to get this derivation, but one of Austrian scientist Guinier, he just used this model and calculated this approximation, and he gave that you can calculate the intensity of Q, and you can correlate the scattered intensity as function of Q as function of I of 0, that intensity what you achieve at angle 0, that is equal to 1 minus 1 over 3 Rg square Q square plus O Q to power 4. So this is the equation he derived. So that intensity is related to the radius of gyration and also the scattering vector. And he further simplified this equation, that this equation actually can be further simplified, that intensity is equal to primary beam intensity I of 0 to the exponent of minus 1 over 3 Rg square Q square. So this is the equation. This is the most important equation for your X-ray scattering, so that you can calculate radius of gyration using this Guinier's approximation. So this is called the Guinier's law. So because this is exponent, so it means what you have here, so you will get on y-axis I of Q, and here on x-axis you have Q square. Yeah, so this this is if you want to make a linearize the equation. So what you will do, so you will take q square here and you will take log natural of I of q. So then you can remove this exponent term of this, yeah. So you take log natural of that. In this case, you will have log natural I of q, and if you plot on x-axis q square, then you should get a straight line because it will be a linear equation, and the slope of the system will be equal to rg square. So here what I have done, so same data, what I have q and intensity of q, what we do, you take square of all the q values, yeah. So in this case, I have like maybe 200 points on q, different angles, and same at 200 points you had I of q. I took q square and I will take log natural of I of q of your system. Then you should get a straight line, and that straight line is quite valid only in this region where it is a small q value. Small q value, this line will be a straight line. And in that small region of q, you do the linear fit. Why do you do the linear fit? The linear fit you do for linear equation to find out the slope. And in this case, your slope will be equal to rg square over 3. So slope will be equal to rg square over 3. And from this, if you multiply the slope with 3 and take the square root of that, that will be your radius of gyration of your system. So in this way, you can have your scattered intensity data, and then you plot it using Guignard approximation, and using Guignard approximation, you can then use find out the radius of gyration. And those radius of gyrations are actually linked to the radius of molecules as well for different molecules. Radius of gyration is different for different molecules, and so the relationship for their spheres or cylinders, they are different. For instance, if you have a sphere, you can calculate rg square is equal to 3 by 5 r square. This is the mathematical geometrical formula that from geometry you can find this formula that how radius of gyration is linked to r. And this is the equation, for example, for radius of gyration related to r square. And if you want to calculate the radius from this one, so you can see radius of gyration you have whatever value you have, so you can simplify this equation. R will be equal to, yeah, so 5 over 3 and then rg square root of that. So that will be your value of rg for spherical particle. And similarly, if you have a particle with spherical shell, so that it has one inner circle and one outer circle. So inner circle has r0, outer circle has ri. So from this relationship, you can calculate the radius from the radius of gyration. And similarly, from all these equations, you can calculate the radius from the radius of gyration. For example, for disc-shaped particles, rg square is equal to r square over 2. So it means from this you can calculate the radius, that you multiply this this one with the 2, and then you take square root of that, and that will be your radius value. So like this, you can calculate all these parameters. And similarly, so what this we have seen so far, so this is like inverse space. What we see as that scattering intensity, what we get is a function of inverse space, that we see small q value, high distance, high q value, small distance. So from that we can calculate the radius, but we can also calculate the particle shape, and that we can calculate also from the same information, that in each molecule, if there are two atoms, for example, carbon and hydrogen, yeah, so this is one pair. So how these all pairs, they are distributed in that particles, that information can be achieved from the scattering pattern. So scattering pattern contains the information about all the pairs present in the system. So whatever the distances are present in the scattering points, yeah, that information is present in that shape, and that is called the how many different pairs in molecules are distributed, and that's called the pair distribution function, that is called P of R, and it is for all the distances between in the molecule, and that depends upon R square, whatever the total distance, radius of the molecule, multiplied by autocorrelation function. And this is, you know, autocorrelation function is nothing else but is the excess scattering length density and the intensity of the system. So this system, yeah, if you do inverse Fourier transform of this system, yeah, so this is called the P of R, period distribution function, that for example, whatever intensity you have got, if you do the, because that is the inverse space, and if we do the Fourier transform, inverse Fourier transform, that will change the inverse space to the real space. So it means if you have I of q sine q of r over q r into dr and q square, that goes from 0 angle to the infinity. If you do the integration of this one, then that is called the inverse Fourier transform with respect to the distance of the system, and that will give you the information about the real system in the real space. So it means now you will not get this kind of intensity curve, but you will see actual distribution of different pairs at different distances. And that's how you have this, for example, this pair, this or IFQ, it has radius of gyration calculated 15 angstrom, and then you do Fourier transform mathematical operation that you integrate this curve using this model, yeah, and then you get the distribution of molecules in your system. So it means at zero distance you have certain molecules, at highest distance you have certain molecules, and this is the distance where you will get the radius of the molecule in the center of this mix. So this bell-shaped curve is achieved from this, for example, from this when we model this, it's a spherical protein molecule lysozyme, and this distance is called the radius of the molecule, that is the 20 xm, that is 2 nanometer particle what you achieve from this system. So like this you can see that this is the pair distribution function, and you can use different AB initio models to calculate the final shape of your molecule. And like this you can calculate the scattered intensity of different shapes of the molecules, and that is expressed here. So for example, if you have spherical particle, this you can see in red, so this will be the scattering intensity pattern look like in the red here. But when you transform this into pair distribution function by doing the inverse Fourier transform, that your software for your X-ray will do it for you, so or other softwares available online that can do Fourier transform for you, that you will get this bell-shaped curve. Yeah, so bell-shaped curve mean the molecules are distributed evenly, and then this distance is called the radius of the molecule, and this maximum distance is the diameter of the molecule. Yeah, so this bell-shaped curve mean you will get it for the spherical particles. But if you have some kind of rod-like particles, what you will see, there will be two lengths here. Yeah, so one maximum you will here, and then it will go the stretched here. Yeah, so this you can see that if you Fourier transform this, so this will be the first distance, that will be the radius of this system, and then the total length of the system, that should be explained by this one. And similarly, if you have a dumbbell shape kind of molecule, so what you will get the scattering intensity pattern, so that will have two areas. Yeah, so one from one side, so this will be for individual units here, that will be for the for the total system of your molecule, the total length of your molecule, and then in this part, higher distance you will get for the individual molecule. And that's how you can calculate Fourier transform this one, and then you can see, you will see two humps in this one, two maximas, one maxima for individual molecule, what will be the radius of this one, and other will be for the total, what will be the total distance of this molecule. And like this you can calculate the different shapes and different sizes. So this is how we calculate this one. And towards the last, we can also calculate the interactions of the molecules from this system. So I will just go this one towards the end. So I will be just maybe 2-3 minutes late because we started a little bit. Is it okay if we just go ahead like 5 minutes extra time? Yeah.
Yes, fine.
Okay. So now we just to explain you that we can calculate the intermolecular interaction between different protein molecules, different polymer molecules, or different macromolecules in a solution scattering system. And those interactions are quite important. For example, if those interactions can be important, for example, in Alzheimer's disease, yeah, where different protein molecules interact with each other and they form some kind of amyloid fiber. Yeah, what kind of interactions they have, that how we can change those interactions, that information gives us quite a useful tool to address different diseases, for example, Parkinson's disease, Alzheimer's disease, etc., cataract disease. And also, for example, if you have to do crystallization of different pharmaceutical compounds, how molecules interact with each other, how their interactions are. If you know those interactions, and if you can modify those interactions, you can design crystals with specific structures. Yeah, and that information can be calculated by using small angle X-ray scattering. So what we do in this case, so when we have single molecule, so in that case, single molecule will scatter intensity, for example, and that is called the form factor of your molecule. But when you have a lot of molecules around it, then molecule will start interacting with each other. So in this case, whatever scattering pattern will you contain, that will contain information about the interaction as well between other molecules. Yeah. So in this case, you get intensity of your molecule, yeah, at different higher concentrations. N is the concentration. So at higher concentration, what you will get, you will not get only the form factor, that individual molecule, but also get structure factor, that how other molecules are structured around it. That is function of concentration. If you increase the concentration, your intensity will go higher and higher and higher. So that is function of concentration. And that also depends upon how molecules will interact with each other. Higher the concentration, higher will be the intensity. So this is the function what you calculate intensity for the case of concentrated solutions. So in this case, what we do, we have to get the information about the structure factor, because structure factor is the factor which gives us the information about the interaction of the molecule. So what we can do is that we measure scattering intensity of very dilute solution, where we see that our scattering is almost from one individual molecule, extremely diluted solution. That will be your form factor. For example, that is shown here. That is the K is the one constant what you can express that contains all the information, excess, scattering length, density, and all the factors what we have seen in the previous equation. But mainly it depends upon the structure form factor and the extremely low dilution concentration. So in this case, there will be no interaction between each other, and structure factor will be 1 for all the cases. So it will be 1 multiplied by form factor, that will be I of Q. And then what you do, then you measure intensity as function of concentration for different concentration. For example, 10 milligram, 20 milligram, 40 milligram, 80 milligram per ml concentration. And then that will contain the information about structure factor plus form factor. So then you divide the concentration at higher concentration divided by initial concentration. So this will be the scattering intensity for higher concentration divided by the lower concentration. And then you see, you cancel all the facts, and what is left here, sorry, here it should be N0, N over N0, that will be your experimental structure factor. So it means you calculate the intensity that measure the experimental data for very dilute solution and for range of different high concentration, and then you divide the intensity of high concentration data divided by the low concentration intensity, and then the ratio of concentration, that will be your structure factor. And that is shown here. If you have random molecules, they will have some scattering intensity, their structure factor will be looking like this. But if you have molecules which have repulsive interactions, and then there are a lot of molecules, they interact with each other, then this will change, that it will show certain kind of ordering in the molecule, because they order at certain distances for them. And this is how you will change the shape of that. Then when you divide this curve by this curve in your Excel file, then you will get this factor, that is structure factor, which is not 1, it is less than 1. It means the probability to find the next atom in this part is 0. Yeah, at high distance, this is Q, at high distance to find the other particle is 0. So they are far apart. Yeah, so at very small distances, at certain distance, you will start seeing that, you will see the probability, and that is actually the where you can see the next particle with each other. And similarly, if you have attractive interaction, in that case, I told you that the molecules become bigger, and then intensity will also become bigger and bigger. And from that, you calculate the S of Q dividing this one by this one, that will be your structure factor. And this is how you will get the distribution of your molecules. And we can calculate the structure factor using this statistical theories, that we can, for any molecule where we know the size of the molecule, yeah, and we can calculate the structure factor from that one. So if different molecules are interacting with each other, they will have some certain kind of interaction potential with each other. So if you multiply the structure factor of one molecule with the interaction potential with other molecules, that will be your total structure factor. You can calculate mathematically, you don't need to do it experimentally. And here structure factor for different molecules which have different sizes, and how many they are, they can be calculated from their packing density, that how many they are. Yeah, and that depends upon their size, that is sigma, that is the diameter of the particle. From this you can calculate the structure factor of your system. Yeah, so this is the mathematical structure factor what you get. And if you multiply this one with your interaction potential, that should be your structure factor. So what you do, what you have calculated here, you have calculated structure factor, and now you know the size already. And now what you do, you start using fitting techniques in your Excel or other, that you provide different interaction potentials to this structure factor what you have calculated experimentally, and you multiply it with the different potentials until you get a curve which totally matches with this curve. That will be your interaction potential of the system. And that you can say that how much potential you gave to the value. And this is, for example, this is the potential what I calculated for this lysozyme molecule at different concentration. and with the salt, and you see this is the depth of the potential, that this much deep well you get 1 to power minus 20 per joule, you will get that potential depth well you will get, and this is the distance at which they feel these interaction. So for example, here I had calculated like very low concentration and very high concentration, and then I divided the data of high concentration by small concentration, and then you get the structure factors. And then what I did, I calculated the size, and from that size I know the number of molecules, their packing density. I calculated S of 0, and then I started multiplying that S of 0 with different potentials and started fitting the curve, because if I multiply your S of 0, so that is your structure factor for a hard sphere, and that will start interacting with each other, and then you will start getting this curve. And in the start it's not fitting nicely, but when you match the potential with this one and this one, then you will see that you get the totally fitting curve. This black curve is the fitted curve, and this green spots are these structure factor for different concentrations. So you have at low concentration, at high concentration, you have different interactions. Low concentration of proteins, they have high interaction, interacting strongly with each other because they are negatively charged. Their interaction energy is more. But in case of high concentration, their energy is small because they are repelling with each other. And similarly, from this is the potential what I use to fit at different distances, that you can see in start it can have lysozyme, you can have very repulsive interaction energy there. But if you keep on adding different salt in this, that screens the charge, negative charge, it covers the charge on it, and then molecules don't repel with each other, and then slowly molecules from repulsive, they start going to attractive interaction. So this below this negative well, this is called attractive interaction, and this is the repulsive interaction. So like this you can calculate the different interaction energies. So this is how you calculate all of this, and I have added this information for one amyloid forming protein which are present in Alzheimer's related diseases. So I have published one paper where we calculate the interaction energies, where insulin forms amyloids, and what are their interaction energies. And that is a paper which you are supposed to read, and that I have added in your documents in your system, in your Canvas. So that you must read and try to understand that what we have done and what is the theory behind it, and that will give you more idea about all of this. Okay, so this is all what I wanted to say. So do you have any question?